Assalamu alaikum. This is lecture number 4, Physics 281. In this lecture, I'll talk about the energy consideration of our previous example, the coupled simple pendulums. I will write the energy in terms of the normal coordinates x capital and y capital. As I said in the previous lecture, the kinetic energy should be some constant times x capital dot square plus some constant c times y dot square, and the potential energy should be at some constant times x capital square plus d some constant times y capital square. So the question is, what's A, B, C, and D? The kinetic energy of the system is given by half m x dot small square plus half my dot small square. Now we can write this expression as m over 2 of x dot plus y dot the whole thing square over 2 plus x dot minus y dot square over 2. X dot plus y dot is x dot capital, and x dot minus y dot small is y capital. So the kinetic energy is m over 4 x dot square plus m over 4 y dot square. Now let's redefine the normal coordinates as x capital sub q equals square root m over 2 times x capital, and y capital sub q equals square root m over 2 times y capital. Invert these two equations. X capital equal square root over 2m x capital sub q, and y capital equal square root 2 over m x capital aq. Take the derivative of x dot and y dot. We get for x dot equal square root over 2m x dot sub q, and y dot capital equal square root over 2m y dot capital sub q. Now insert these in the kinetic energy form. We get this expression. Simplify. There is some cancellation, m by m2. We left by 2 here. So the kinetic energy is half x dot square sub q plus half y dot square sub q. Now for the potential energy, we have the potential energy for the right pendulum. If we take the minimum point of oscillation as 0 as a reference for the potential energy of the gravity, then the potential energy for the right pendulum is mgh. H is mg of L minus L cosine theta. We have also potential energy of the same form for the left mass, and we have the elastic energy of the spring. So the potential energy consists of 3 terms. Now let's simplify this term first. The potential energy for the right mass, which is mg sub L of 1 minus cosine theta. I push this L outside, and then expand cosine theta as 1 minus L x as 1 minus theta square over 2. Then 1 minus 1 is 0, minus minus is a plus, so we left with mgl theta square over 2. Now for small angles, theta is x over L, so we get finally mgx over 2L for the right mass. Similar expression for the potential for the left mass, but we have to replace x by y. Hence the potential energy is mg x square over 2L plus mg y square over 2L plus the elastic energy of the spring, or the energy stored in the spring, which is half kx minus y square. Now this thing can be written as mg over 2l of x squared plus y squared plus half k y squared. Now we can do this expression as we did in the case of kinetic energy. We split it into two parts, x plus y squared over 2 and x minus y squared over 2, and recognize that x plus y is x capital and x minus y is y capital. So we get mg over 4l of x squared plus y squared plus k over 2 y squared, which is equal mg over 4l x squared plus mg over 4l plus ky into y squared. Now we have to use the new definition of the normal coordinates x sub q and y sub q. Insert this in the above equation. We get this form half g over l x squared sub q plus half g over l plus 2k over m times y sub q squared. This is omega 1 square and this term is omega 2 square. So we have for the potential energy half omega 1 square x square sub q plus half omega 2 square y square sub q. Now the total energy is kinetic energy plus potential energy. Add the two terms, we get half x dot square sub q plus half omega 1 square x square sub q plus half y dot square sub q plus half omega 2 square y sub q square. We have two modes here, two modes, and there is no cross products like x sub q, y sub q in the energy expression. Thank you.